about the interrupts in 8051 microcontroller. Yes. So when we talk about interrupts in 8051 microcontroller, this is the interrupt structure of 8051 microcontroller. What you are able to see in the screen. Are you able to see the screen?
Yes, sir.
Okay. So what do you mean by interrupt? Okay. Interrupt means disturbance. Am I right or not? What do you mean by interrupt? Interrupt means disturbance. Is disturbance necessary? The question comes to our mind is disturbance necessary? The answer is yes, as well as the answer is no. So very simple. We are talking about interrupts. Interrupt means disturbance. Is disturbance necessary is the question. If so, the answer is yes, interrupt is necessary in some cases. Interrupt is not necessary in some cases. So we have to identify when the interrupt is needed and when the interrupt is not necessary. Something like that. For that, let us take a good example of a mobile phone. Because when we give a real-time example, which will be more convenient for all of us to understand interrupts. So let us take a mobile phone. In a mobile phone, we are listening a pleasant music. So it is something like a main routine. Let us say, for example, it is something like a main routine. So listening music. So by the time if someone called, the incoming call is an interrupt to the mobile phone. But the mobile phone doesn't think that, okay, our owner is listening a good music. If we interrupt the owner and saying that somebody is calling, it will be a big disturbance to our owner. So it is better not to disturb, something like that. Mobile phone is not deciding that. Simply mobile phone is interrupting and saying that somebody is calling. So why mobile phone is interrupting? Because the incoming call is having highest priority when compared to the listening music. So here the word priority comes into the picture. If the interrupt is having highest priority, then interrupt should be allowed. If the interrupt is having lowest priority, then interrupt need not be allowed. That is a very simple status to start with. So whenever there is an interrupt means there comes the priority. So with respect to the current work, if there is some highest priority work comes means we have to do that highest priority work. With respect to the current work, if some other lowest priority work comes means we will postpone that lowest priority work, because when compared to the lowest priority work, the current work itself is having highest priority. Hence we must do the highest priority work. So doing highest priority work is the prime objective. So that means executing the highest priority task is the prime objective of a microprocessor. So which is having highest priority, that need to get executed, which is having lowest priority, that need to wait. That is the fundamental thing with respect to interrupt we need to understand. So with this example, by listening music is having lowest priority when compared to incoming call. Hence incoming call is having highest priority. Hence it is being allowed. Then choice is given to the user that whether I can continue listening music or whether I can attend the call. The priority goes to the user. So if the user presses green button means user is considering the incoming call as highest priority. If the user declines the call means with respect to the user, the incoming call is having lowest priority when compared to the listening music. But mobile phone has to interrupt and say that, okay, there is an incoming call. Then the priority choice is given to the user that whether the user feels listening music is having highest priority, let him listen the music. If user decides incoming call is having highest priority, then user can decide the incoming call. He can as highest priority and he can answer the incoming call. Okay. So when compared to the listening music, incoming call is having highest priority, hence is attending the call. While attending the call, if some other new call comes means that is also an interrupt. But the mobile phone should not think that already we have interrupted our owner, already the music is muted and our owner is discussing with somebody else. Now we should, why we should interrupt? Something like that mobile phone should not think. Mobile phone somehow it cannot ring also because he is in conversation. While we are in conversation, the mobile phone should not ring, even it is 500 rupees mobile phone or 50,000 rupees mobile phone. While there is a conversation, mobile phone should not ring. And somehow it has to notify that there is a new incoming call. So better way is to give some beep beep sound in the loudspeaker. to interrupt that there is no incoming call. So that beep beep sound is an interrupt to the user saying that there is new call coming. Then again, choice is given to the user that whether I can give if I feel the incoming call is having highest priority, he can attend the incoming call and be putting the current call in hold, or vice versa. Okay. So let us assume that the second call is having highest priority. So the user put the first call on hold and he is answering the second call. By the time he is talking with second call, the battery low notification comes. So already there are so many interrupts. So the battery low notification comes from the internal battery. So the microprocessor has to think, okay, already we have disturbed it twice. The third time, why should disturb? Something like that mobile phone should not think, because battery low notification is having highest priority among all this. Somehow it has to notify that battery low notification has come, whether you are listening music or whether you are talking to the first person, whether you are talking to the second person. Anyway, it is going to end up soon because battery is getting low. Whatever you are doing, let her complete it as soon as possible because the battery is very low. Something like that. It has to notify the battery low through music or through a display, etc. It's very interesting. So here from this example, we can understand battery low notification is having highest priority when compared to the second call. Second call is having highest priority when compared to the first call. And first call is having highest priority when compared to listening music and lot more with respect to the simple our mobile phone understanding. Okay. So interrupts are mandatory. Why? Because interrupt helps us to do something in a best way. Hence, to do the highest priority task, we need interrupts. So let us take another example in a classroom, right? So we are discussing the class and we feel that nobody should disturb the class. We have closed all the doors and the class is happening. And if somebody knocks the door, that itself is a big disturbance. And we will never allow somebody to enter if the class was started. So because entering and leaving is a big disturbance to the people, those who are listening as well as those who are teaching. That's why entering and leaving is not allowed. That's why we close the door. In that context, disturbing the class is not good. But the worst case, there is some emergency fire outside and somebody is knocking the door to make all of us to run away from the classroom. By the time we should not say, no, 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 we will attend the class. The interrupt is very important. Hence, I will attend the class. Somebody is shouting from outside, there is a fire, sir. You have to run away. No, 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 I will attend the class. Means this is the foolish thing. They will shout from outside, right? First you have to be alive, then only you can do some interrupts. Better run away. There is a fire, something like that. They will shout from outside, no? So the fire information is having highest priority when compared to listening class. That's why disturbing the class is allowed, because we have to run away from the class to save ourselves. But just like that, coming late to the class and disturbing the class is having lowest priority. Hence, it need not be allowed. In that context, we can we can relate the interrupts. And in other context, with respect to our college environment, principal is like a processor. And whenever the student is waiting to meet principal, he is having lowest priority. By the time when student is discussing with principal, any faculty comes, the principal will ask the student to wait. A faculty has come, let me discuss with him. Then later on I'll talk to you, something like that. Principal will inform the student to wait when the faculty comes. So that's very interesting because the faculty member is having highest priority when compared to student. And some HOD comes means, then again principal will say, okay, a faculty member, please wait along with that student. HOD has come, let me discuss with him and then let us do something. So HOD is having highest priority when compared to the faculty member. And the dean comes means, so HOD will ask the dean to wait, and principal will ask the HOD to wait, and the principal will talk to the dean, something like that. It goes on because dean is having highest priority when compared to HOD is having highest priority when compared to the faculty member, and faculty member is having highest priority when compared to the student, something like that. It goes on. So priority comes into picture, who is having highest priority, that need to be served. That is the moral of the complete discussion. Now, with respect to interrupts, with respect to microprocessor environment, Every work is nothing but the execution. So highest priority task need to be executed first. All other lowest priority task has to wait, something like that. So when we talk about interrupts, interrupts are broadly classified into hardware interrupts and software interrupts. Interrupts are broadly classified into hardware interrupts and software interrupts. If we talk about hardware interrupt means the interrupt which happens in the pin is called as hardware interrupt. The interrupt happens internally by setting some flag, etc. is called software interrupts. So first let us understand the hardware interrupts. Then it will be easy for us to relate with the software interrupt. So what is hardware interrupt? Interrupt which happens in the pin is called as hardware interrupt. So in the pin, if interrupt happens means in interrupt, what are all the possibilities? That means in pin, what are all the possibilities? The pin can be in either logic 1 or pin can be in either logic 0. So the the present state of the pin, whether it is logic 1 or logic 0, that can also be treated as an interrupt, which we call it as level triggered interrupt. Level 1 triggered interrupt as well as level 0 triggered interrupt. Or there is a possibility for us for the pin to transition from 1 to 0. And there is a possibility for the transition from 0 to 1. So the transition from 1 to 0 can be treated as falling edge, and the transition from 0 to 1 can be treated as rising edge. So they are all coming under edge triggered interrupt. Other than these four possibilities, there is no possibilities of a hardware interrupt with respect to a microprocessor or microcontroller. So this is the moral which we need to understand. So this is applicable to the microprocessors and microcontrollers which was invented before 2020, or this will be applicable to the processors and controllers which is about to implemented after 2020. If the interrupt is happening in the pin means there are only four possibilities. It can be a level 1 interrupt or it can be a level 0 interrupt, which is called as level triggered interrupt. It can be a falling edge interrupt, that means a transition from 1 to 0, or it can be a rising edge interrupt, that means a transition from 0 to 1, which is called as edge triggered interrupt. So interrupt which is happening in the pin broadly classified into two. One is level triggered interrupt and edge triggered interrupt. Level triggered interrupts are classified into two, level 1 and level 0. Edge triggered interrupts are classified into two, falling edge and rising edge. So other than these four possibilities, there is no possibilities for any micro of interrupts, hardware interrupts. That is the moral of the discussion. So when you name any microcontroller, SPIC microcontroller, 8051 microcontroller, TIVA microcontroller, ST microcontroller, 32-bit microcontroller, 16-bit microcontroller, 8-bit microcontroller, any microcontroller, whenever they talk about the interrupts in the hardware, that means interrupts happening in the pin means these are all the only four possibilities. So we should not discuss that interrupt in 8051, interrupt in PIC microcontroller, interrupt in MSP 430 microcontroller, interrupts in TI microcontroller. This interrupt is common. So these are all the only four possibilities that we need to understand. That's why this many times I'm repeating. With respect to 8051, because it is better to start with the simple 8-bit controller, that is why we are focusing towards 8-bit microcontroller. Now our focus is how this interrupt works in 8051 microcontroller, especially hardware interrupt. That is the idea. So I believe now we are very clear about the interrupts, which is hardware interrupt. So let us see how the hardware interrupt is working in 8051 microcontroller, and let us experience it for better convenience. Okay. So if you look at the interrupt structure of 8051 microcontroller, look at the screen. So 8051 microcontroller can support two hardware interrupts. That means there is an INT0 pin and INT1 pin. If you look at the pin diagram, there is an INT0 pin and INT1 pin. That is the 12th pin and 13th pin. That is P3.2 and P3.3 are the two interrupt pins with respect to 8051 microcontroller. So the internal interrupt structure is shown here. So INT0, there is a bar symbol. So what is this INT0 bar and what is this INT1 bar? So the bar indicates it is level 0 type of interrupt. If there is no bar means it is level 1 type of interrupt. So among two possibilities of level triggered interrupt, that is level 0 and level 1, 8051 can support only level 0 type of interrupt. 8051 cannot support level 1 type of interrupt. Okay. So there are two hardware interrupt pin. INT0 pin, INT1 pin, which is P3.2 and P3.3 pin, which is P3.2 and P3.3 pin, which is acting as a level triggered interrupt pin, and that too it is level 0 type of interrupt. So what is level 0 type of interrupt means? This interrupt is applicable to the applications which demands as long as, this is very important, as long as, whenever the application requirement is something like as long as, then we need to use only level triggered interrupt. Say for example, let us consider the reset. Reset is active high in 8051 microcontroller, as we all know. Reset is active high in 8051 microcontroller, as we all know. So we can say as long as the reset pin is active high, the microcontroller remains in reset state. Shall we say like this? It's very interesting. So the reset is active high with respect to 8051 microcontroller. So as long as the reset pin is in logic 1 state, as long as the reset pin is in logic 1 state, microcontroller remains in reset condition. Something like that we can say. It is very easy for us to understand the significance of level triggered interrupt by comparing with the reset pin. So something like reset, that is as long as, whenever application demands as long as, for that kind of applications we need to use only level triggered interrupt. Okay, so INT0 is the level triggered interrupt, level 0 type of interrupt. INT1 is level 0 type of interrupt with respect to 8051 microcontroller. And let us experience this. Let us experience this first, then slowly we'll go to the next part. So if you look at the interrupt structure of this 8051 microcontroller, you can understand very clearly. I am zooming in. So when you enable this interrupt, there is something like IE0 flag. There is something like IE0 flag. This flag will set. This flag will set. So whenever the interrupt happens means, and there is an inverter, you see, when you make this 0, when you make here as 0, that means when you are creating an interrupt by putting it 0 means, so it is complemented, it will become 1, and IE0 will become 1. By whenever the interrupt happens means IE0 bit will become 1. That is the first thing we need to understand. So when we talk about interrupt means what? It is jumping from the main routine to the interrupt service routine. So for that we need to enable the interrupt. To enable the interrupt, there is a register called IE register. What is IE register? Interrupt enable register. So this in you using this interrupt enable register, we have to enable this external interrupt 0. So let us say this is external interrupt 0. So to enable this external interrupt 0, we have to close this switch, then we have to close this switch. So two switches must be closed. That means some 2 bits need to be made as 1 in IE register. What is IE register? Interrupt enable register. In interrupt enable register, 2 switches must be closed. One switch is called as EA, that is global enable, which is called as global enable. That means if EA equal to 1, each interrupt source is individually enabled or disabled by setting or clearing its enable bit. So EA must be 1 to enable all the interrupts. So this most significant bit of interrupt enable register should be 1. And in this interrupt enable register, EX0 means it is external interrupt 0, and EX1 means it is external interrupt 1, which is INT0 and INT1. Our interest is to enable external interrupt 0, hence INT0, hence this bit need to be 1. So to enable all the interrupts, this has to be 1. So 1 0 0 0 0 0 0 1, that is 81 should be the interrupt enable register value to enable the global enable interrupt bit, as well as to enable the external interrupt 0 bit. That means to close these two switches. To close this switch is global enable. You can see it is a common switch to close all these switches together, which is called as global enable. So this global enable switch will get closed only when EA equal to 1, and this individual switch will close if external interrupt 0 is 1. So to make this happen, 81 is the hexadecimal value which we have to load it to the IE register. Then whenever interrupt comes, program execution will go to the, will create an, that means this pin can create an interrupt to the microprocessor. That's all. So by making 0 in this pin can create the interrupt, can create an interrupt to the microprocessor. So then interrupts are vectored interrupts and non-vectored interrupts. So that we must know. So what do you mean by vectored interrupts? So if the interrupt has some address, then it is called as vector interrupt. For example, look at the screen. If there is an external interrupt 0, then it has a vector address of 0003. If there is an external interrupt 1, then we can say the vector location is 0013. So what do you mean by 003 and 0013 means? So whenever this interrupt happens, what need to be done, that has to be written from this location. Okay, once again I repeat, whenever interrupt happens, what need to be done, which has to be written from that vector location. So for example, if external interrupt 0, because it is level 0 type of interrupt, no? So whenever the logic 0 interrupt comes here, so when the interrupt becomes 0 means this flag will set and it will interrupt the microprocessor. Then microprocessor execution will jump to 0003 location. So from 0003 memory locations of program memory, this is very important. So program memory location 003, we have to write some program. That program should execute whenever that interrupt happens. Say for example, so this 0 is something like fire notification. So from the fire sensor, 0 comes means what? As long as it is 1, there is no fire. When it becomes 0, there is a fire accident happens, something like that we can understand. So when it becomes 0, then what happens? Because we have enabled the external interrupt 0 interrupt, which is having highest priority, let us assume, and it will create an it will interrupt the microprocessor, and microprocessor execution will come to 0003 location. In 0003 location, what program we need to write? We need to write a program in such a way that it has to switch on the emergency alarm. Because if there is a fire means we have to switch on the emergency alarm, and we have to open the emergency door, and we have to call the fire service. So those instructions that we have to write from the memory location 0003. So that is why whenever interrupt happens, what need to be done, that has to be written in the interrupt vector location. Something like that we need to understand. It is fantastic, right? It's a very important thing we need to understand. So because interrupt is having highest priority when compared to the main routine. So normally main routine will get executed. Whenever interrupt comes, program execution will jump to the interrupt vector address. So at that address, what need to be done when interrupt comes, that need to be written. That is the fundamental understanding we need to have. So with respect to 8051, these are all the interrupts and these are all the vector locations as shown on the screen, out of which we are interested in looking at only external interrupt 0, and we are going to write a code and then we are going to experiment it to for better clarity. So now we are very clear about external interrupt 0, that too it's level triggered interrupt, that is level 0 interrupt. And as we all know, level 0 interrupt means as long as the application, as long as, then when interrupt comes, program execution will jump to 0003, which is 003 is the vector address of the external interrupt 0 with respect to 8051 microcontroller. Hence, we have to write some program in 003 and we have to write some main program. So the program that what we write in this location is called as service routine. Why it is called service routine? Because it is not the main one. Whenever there is a fire, then only fire alarm has to produce sound and emergency door need to be opened, fire service need to be called. If there is a service request, then you have to do the service. If not, there is no need for that service. Hence it is called as service routine. Because the service routine is having highest priority, this routine is written in an interrupt. Hence it is called as interrupt service routine, ISR. So normally people will say ISR, interrupt service routine is the interrupt service routine for extra interrupt 0 is written in the vector address 0003. This is how we need to understand. So let us write a code in a KEIL IDE for better understanding. So for understanding, we will start from the beginning. We should start the code from hash include reg51.h and void main is our regular way of doing things, and while one, let us blink our port 0 in the main routine for simplicity. And we can write an interrupt service routine, something like this. We can write an interrupt service routine, something like this. Void, let us say external interrupt 0, interrupt 0. So this is the interrupt service routine where I am blinking port 1. That is port 1 equal to 1's complement of port 1. So as long as there is a main routine, port 0 will blink. So whenever the interrupt comes, port 1 blink. So this 0 has its own significance. When it is 0 means it will go to the external interrupt 0. The number 0, that means lower the number, higher the priority. That we need to understand. Lower the number, higher the priority. So this is number 0, this is number 1, this is number 2, interrupt number 3, interrupt number 4, interrupt number 5, and interrupt number 6. So when you put 0, automatically it go to the vector location 0, 0, 0, 3. When we put the number as 1, it will go to the vector location 0, 0, 0, b. When you put number 2, it will go to the vector location 0, 0, 1, 3. So this vector number is more convenient. Why? Because we don't need to remember this address. That is why the convenience in C programming. So because we have written 0, that is among all these interrupt, extra interrupt 0 is having highest priority. Hence we put the number 0 here. Okay, so let us simply execute this code and we can understand. Now the fundamental idea which we have to think is main routine is having lowest priority and external interrupt is having highest priority. That alone we need to understand. So now you look at the screen. Now you look at the screen. If you look at the screen, here we can see the disassembly window. It's very interesting, right? Now let us run this code. Now the program counter is pointing the 6th line because this arrow mark means it's a program counter which is pointing the 6th line. Port 0 should blink. So let me run this code. You can see port 0 is blinking. So we have to create an interrupt. Creating interrupt means what? Creating interrupt means what? In P3.2 pin, we have to create logic 0 because it is level 0 type of interrupt. In P3.2 pin, we have to make it as 0. If P3.2 becomes 0, then it will create an interrupt according to this interrupt structure. So INT0 is P3.2. When this becomes 0, IE0 flag will set. So when the flag sets means it can create an interrupt, something like that. So for that, we need to enable the interrupt. For that, we need to use IE register. In IE register, we have to set the two bits. Which bits? Global enable bit as well as external interrupt 0 bit. As like we have discussed, this is global enable bit and this is external interrupt 0 bit. So this we have to make it as 1, this we have to make it as 1. And the hexadecimal equivalent of all this is 10000001. So 81 is the interrupt enable register value to enable the external interrupt 0. So to enable the interrupt, what we need to do, we need to write a, we have to initialize the interrupt. How to initialize the interrupt? The fourth line, we have to write IE equal to 0x81. So if we get IE equal to 0x81, extra interrupt 0 will get enabled. That means these two switches will get closed. Which two switches will get closed? These two switches will get closed. So now the interrupt is enabled. So when you make this as 0, interrupt will get created. That is the one we need to understand. So for convenience, there is a simulator. With the help of simulator, we can learn more. With the help of simulator, we can learn more. So if you look at the peripheral, there is an interrupt. If you look at the peripheral, there is an interrupt here. Here you can see P3.2 pin is INT0 bar. Look at the screen. P3.2 is INT0 bar, where the vector location is 0003. Similarly, P3.3 is INT1 bar, where the vector location is 0013. It goes on. So now the program counter is pointing the fourth line. Now you can see, now it is going to get execute IE equal to 81. 81 means what? This EA, global enable, has to become 1 and IE 0, that is global enable has to become 1 and external interrupt 0 is the request has come. That is, it is enabled first. Request has not yet come. So this enable bit need to become 1 and EA bit need to be 1. Let us see after executing the fourth line. Extra interrupt 0 is being enabled and enable all and P3 point interrupt is enabled now. So now if we are running this code, port zeros keep on blinking. Why? Because only lowest priority. It is something like listening music. It is something like listening music. Now we have to create an interrupt. How to create an interrupt? We have to make P3.2 bit as 0 because it is level 0 type of interrupt. So for that we have to take the GPIO pin of port 3. So this is port 3 pin. So now we see the we have to check this port 1 equal to 1's complement of port 1 is written in the vector location 0003. That I have to ensure. Yes or no? This has to be written in the memory location 0003. Let us go to the disassembly window. I can see the 0003 location. If you observe this carefully, in 000 location is the main routine starts. Here it is jumping to start up 800 location. So the main routine is jumping to, that means whenever the microprocessor is reset, the program counter will be there at 0000. So program execution starts here. So at 000, the long jump instruction is used. So the program execution will jump to 800. So from 800, the main routine continues. But if you observe carefully, the vector address is 0003 for external interrupt 0. So in the vector location 0003, again there is a long jump to 814. So that means what? When interrupt comes, program execution will come to the vector location 0003. In 0003, we have used the long jump instruction to 814. So 814th location, if you go to the 814th location, there we have the 814th location, there we have vector location, something like that we can say. 814th location, we have a vector address. Let us go to the 814th location, somewhere around this. You can see 814. So this 814 is the vector location. You can see interrupt service routine. Okay. So why it is jumping? The question comes. Why it is jumping from 000 location to 800th location? Main routine, you can see. Main routine is 800. You can see 800th location. This is the main routine. But the interrupt service routine is jumping to 814. Why? Because the space, if you look at the vector location, space between the 000 location and 003 is only 3 bytes. If the main routine is not jumping from 00 location to 800 location, it can overwrite the vector address. Main program will overwrite the vector location address. And why vector location is jumping? Because there are only 8 locations for extra interrupt 0. Then timer 0 interrupt vector address will come. So in the timer 0 vector address, interrupt service routine for extra interrupt 0 should not be written, overwritten. So to prevent that, whenever the interrupt comes, it will come to this location. From here, you are jumping to some other location, and then if the program is lengthier program means, we can jump to some other location, then we can make use of it. For that purpose, from 0000 location or from 0003 location, it is jumping to some other location and then it is executing. Other than that, there is no reason. There is only very less space. So main routine should not overlap with the interrupt service routine. That's why main routine is jumped to 800th location. The interrupt service routine should not overwrite with another interrupt service routine's program memory address. That is why we are jumping to the some other memory locations. That's what. So those things we don't need to worry about it, because when we write a C program, these things are taken care by the compiler, KEIL IDE itself. But we need to understand, whenever the interrupt comes, program execution goes to 0003 vector address. In the vector address only we are jumping to 814. In 814 only, the interrupt service routine what we have written, is port 1 need to be complemented. So that's what we are doing, right? In 814, port 1 equal to 1's complement of 814. This is extra interrupt 0. So XRLF port 1. Something like that we need to understand. Okay, now the theoretical discussion is 100% clear. Now we have to experiment this. That's all. So now I am running this code. So it's keep on running. So port 0 is keep on blinking. Now to create interrupt means what? P3.2 has to become 0. When P3.2 becomes 0 means what? External interrupt 0 will get created. So because already all the interrupts are enabled, program execution will come to vector location 0003. From there it will jump to 814th location and this will get executed. And after that, there is something like, you see, return interrupt instruction, RETI, return interrupt instruction execution. So after executing the return interrupt instruction, it will jump back to the main routine. Now the question comes, okay, suddenly if the interrupt comes, the program execution will jump to 0003. Then when the return interrupt is get executed, where will be the return address stored? That question will come. So the return address will be stored in the stack. Now the stack comes into picture. What is a stack? Stack is a portion of a data memory. Whenever the program execution is jumping to the interrupt service routine, the return address will be pushed to the stack automatically. After executing the return interrupt instruction, the return address will be popped from the stack. That we are going to experiment it now in a very clear way. Now let us see. We are creating an interrupt, right? Now I am creating an interrupt P3.0, 3.1, 3.2. So I am creating an interrupt, level triggered interrupt. It has become 0. So now you have to observe very carefully because it is very, very important. Now what happens? What is the program counter content? Program counter content is 812. The program counter content is 812. So here what in 812, what is the assembly language program written? Short jump 80F. What is 80F? 80F is again complement port 0. So as per this instruction, the program counter has to be loaded with 080F. According to this instruction, it has to jump to 080F. So this is the program counter. Program counter has to become 080F according to this instruction. That is, this is main routine. Why it is jumping? Because of while loop it is jumping. So that's why port 0 is keep on complementing. When it jumps to 0x0 only, XRL port 0 will happen. Again it will come here, 0x0F, XRL port 0 will happen because our main routine is this, as we see here. So because the while loop is over, again it has to come back here. That's why short jump is the code we have written, as we all know very well. So now it's very important because we have created an interrupt. The program counter will not be loaded with 080F. Program counter will be loaded with the vector address of external interrupt 0, which is 0003. That we have to ensure this by doing single step execution. So look at this program counter. Now I'm highlighting this in the screen. Now everyone have to look at the screen, which is very important. Now the program counter's address is 812. So the program counter is pointing. So the yellow color mark itself is program counter. So program counter is pointing 812. As per the main routine instruction, short jump, it has to jump to 080F, which is this location. Instead of jumping to 080F, it has to jump to vector address of external interrupt 0, which is 0003. Why? Because interrupt is having highest priority when compared to the main routine. Now the interrupt has come, so it has to jump. Program execution has to go to the interrupt service routine. Interrupt which has come is external interrupt 0. The vector location of external interrupt 0 is 0003. Hence the program execution should jump to 0003 now. So let me do the single step in the execution. What we are supposed to observe is program counter must become 0003, which is the vector address of external interrupt 0. Now what we can understand is, now I'm making P3.2 as 0. By making P3.2 as 0, what do I say? There is a fire. I'm saying that something like a fire. So it has to go to the interrupt service routine and it has to toggle port 1. So toggling port 1 is nothing but fire alarm. Something like that we can say. So for that it has to jump to 0003. So now we are supposed to check program counter as 0003. You see? Sorry, just a minute. It has to come to, now we are expecting program counter has to become 0003. Now I am executing from the C program side. I have to execute from the assembly program side, then only it will be very interesting. Okay, let me finish up this and come back. Okay, now I am creating an interrupt. You see, now I am creating an interrupt P3.2. Now program execution has to go to 0003. You see, program counter has gone to 0003. See, 0003. Here, from here you are jumping to 814. From here you are jumping because there is an instruction called the long jump 814. So now I am doing single step execution 814. Let's come to 814. There it is toggling port 1 equal to, once complemented port 1 means XRL. So already port 1 is logic 0 here. It will become 1. You see, it will become 1. It has become 1. After that you are returning from interrupt. So where to go back? It has to go back to, we do not know because we are in the ISR. So look at the stack. Okay, now I will show you the stack. Where is the stack pointer? Look and see where is the stack pointer. Stack pointer is pointing 09. You see, this is the stack pointer which is pointing 09th location. What is the initial value of a stack pointer? Initial value of the stack pointer is 07. That we need to understand. There is a possibility for us to see the memory location. So this is code memory, and there is a possibility for us to see the data memory also by putting it as D colon 0x00 means it will show the data memory. So in the data memory, the default stack pointer will be pointing 07. Whenever the program execution jumps to the interrupt service routine, stack pointer will be incremented and the return address will be stored. Okay, stack pointer is pointing 07. The first increment is 08. Let me put it as 08. First increment is 08. In 08 there is 0f, and 09 it is 08. So 080f is the return address. So look at the screen, look at the cursor. 0808f is the return address. After executing RETI, program counter will become 080f. That we need to observe. And we must see the stack pointer should become 7, because after executing the return interrupt instruction, program counter is pointing 09. So in 9, 08 is there. That is getting popped. Then program counter will be decremented by 1. And the content of 08 will also be popped because the lower order address. So 080f is the total 16-bit address. Again, stack pointer will get decremented. So stack pointer will come back to 07. So when you execute the one line, stack pointer will become 07. Program counter will be reloaded with the return address, which is 080f. And we can see 080f. Program execution will jump to the main routine. That we need to understand. So now I am doing the single step execution. You see, I am doing the single step execution. It has come to the main routine where the 0f0f location was there. You see, stack pointer has become 07th location, and 080f has come to the program counter, and the pointer has come here. So that means program execution is returned from interrupt service routine to the main routine. And as per our discussion, always the main routine, in the main routine, only one instruction will get executed. In the main routine, only one instruction will get executed, and it will check for interrupts. Again, there is an interrupt because it is a level triggered interrupt, because you have made P3.2 as 0. Again, the interrupt was there. Once again, the same process will get repeated. Stack pointer will be incremented, and the return address will be pushed to the stack, and the program execution will jump to 003 vector location, and the vector address, the program ISR will execute. Let us see this. Now what happens? Now it has to execute only one instruction. Now you have to see it has to execute only one instruction. Now you see it has to execute 080f. After executing one instruction, it will check for interrupt. Yes, is there an interrupt? Yes, there is an interrupt. So some highest priority task is waiting. So it is better to service the interrupt. So what happens? Now the program counter is pointing 812. Here again you are saying at 080f, but instead of going to 080f, it will jump back to 0003. Why? Because 0003 is the vector location, because interrupt has occurred. So it has to go back to the interrupt service routine by pushing the return address into the stack. Now the return address is what? 812, because now it has to jump to the interrupt service routine. After completing interrupt service routine, it has to come back to this line. So 812 is the return address. So 812 will be pushed to the stack instead of 080f here in the screen. If you look at the screen, the data memory location 080f, data memory location 080f. This will become 812 if you observe carefully. So the return address will be pushed to the stack, and the program counter will be loaded with 0003. That is the one which you have learned in theory. Now you can experience in the simulator. So once again I repeat, interrupt has occurred. It has executed one line of code. While executing one line of code in the main routine, it will check for interrupt. Yes, there is an interrupt. Because there is an interrupt, it will jump to the interrupt service routine by pushing the return address into the stack. This is the return address. So return address is 812. 812 will be pushed to the stack by incrementing the stack pointer by twice, and the program execution will go to 0003, which is a vector location for external interrupt 0, because external interrupt 0 has occurred. Let me do that. Let me execute that and show you. Now I'm doing the single step execution. Now you can see program execution has come to 0003 location. From here you are jumping to 814 location, and from 814 you are toggling. Now the port 1 is 1. The port 1 will become 0. You can see port 1 will become 0. This port 1 has become 0. Again, you are returning back to the main routine. Yes, you are returning back to the main routine. G0 is 0F. And again, you are XRing L. Again, the interrupt is already there. Again, it has to come to the ISR 000. You can see it has come to 0003. Here again, it is toggling port 1. And again, going to the main routine, toggling port 0. So one thing we must understand here it is, after returning from interrupt, only one instruction will execute in the main routine, and then it will check for interrupt. If interrupt is the continuing means, it will go to the ISR, it will execute. Because there is only one instruction in our 851 in our main routine. That is why it looks like both the interrupt service routine and main routine both are running. So now let me run this code. You can see port 1 is also blinking, port 0 is also blinking. That means both the main routine and interrupt service routine is executing because interrupt is extra interrupt 0 is enabled. If you observe carefully, as long as P3.2 is 0, the ISR is getting executed. That means as long as there is a fire, the fire alarm is keep on producing sound. So what is fire alarm? The blinking of port 1 is a fire alarm. So the port 0 blinking is main routine. Port 1 blinking is interrupt service routine. So now the interrupt has occurred because it is level 0 interrupt. As long as there is a level 0 interrupt, so this will keep on blinking. So now when we see, if I make it as 1, the interrupt is deactivated, then port 1 will not blink. See, port 1 is not blinking. Only main routine is getting executed. So whenever interrupt is there, then interrupt service routine will get executed. So the blinking of port 1 is the interrupt service routine what we have written here. You can see. So port 1 has to blink. That is the service routine we have written. So that is why port 1 is getting blinking as long as there is an interrupt. Because it is level triggered interrupt as discussed, as long as there is a level triggered interrupt, interrupt service routine will get executed. So because it is quickly happening several thousand times in 1 second, so that's why you are not able to observe this carefully. So as long as it is 0, the interrupt is happening. That is the moral of this discussion. Okay, so this is how your level triggered interrupt works. And as we discussed already, as long as whichever application demands, as long as this level triggered interrupt will work, that has been discussed, I think 100% because it is simulated and you are very clear about it. And because there is a hardware interrupt, there is one more segment is pending. We'll do that also. So there is an edge triggered interrupt. So how do we enable the edge triggered? So like level 0 interrupt, level 1 interrupt is there in the higher end microcontroller. It is up to us to, there will be some selection bits, whether I am enabling level 0 interrupt or level 1 interrupt. With respect to 851, there is only level 0. There is no possibilities of level 1 interrupt in 851. And similarly, with respect to edge triggered interrupt, there is a falling edge interrupt and there is a rising edge interrupt. There is a falling edge interrupt and there is a rising edge interrupt. Among these two, only falling edge interrupt only 851 can support. As you see in the screen, falling edge interrupt alone 851 can support. 851 cannot support rising edge interrupt. But how falling edge interrupt works, in the similar way, rising edge interrupt will also work. Let us see how to enable this falling edge interrupt. So you see there is one bit called IT0 bit. What do you understand from IT0 bit? This is the bit which can enable the external interrupt as level triggered interrupt or edge triggered interrupt. Okay. So when this bit is 0, the external interrupt is in level 0 interrupt. When we make this IT0 bit as 1, this switch will come here and then it will make it as a edge triggered interrupt. So that means whenever there is a falling edge, it's very important. It is not rising edge with respect to 8051. Whenever there is a falling edge, whenever there is a transition from 1 to 0, the IE0 flag will set. And as usual, through IE register, if you have done the global enable as well as extra interrupt 0 enable, interrupt will get created and ISR will execute. But here, for every edge, every falling edge, ISR will get execute only once. So in the level triggered interrupt, we talked about as long as it is 0, the program execution will keep on executing the ISR as like how we see. But for falling edge, for edge triggered interrupt, as many number of edges will execute as many number of times, execute the ISR that many number of times. Hence, edge triggered interrupts are mainly used for counting purpose, something like that people used to say. Let us experience that. Now we are very clear about the interrupts, then very quickly we can experience the falling edge interrupt. Only thing is we have to make IT0 as 1. If you make IT0 bit as 1, this switch will come here. So then INT0 will become falling edge interrupt. The rest of the thing remains same. So only small change we have to do it in the code. After enabling the external interrupt, we have to make IT0 as 1. This will enable the edge triggered interrupt of extra interrupt 0. Rest of the thing is clear. And now we will check the interrupt structure in a more better way. Now we can see as usual IE equal to 81. When IE becomes 81 means what? As usual, if you see when IE becomes 81 means what? Enable all, and IT0 means it will become edge triggered interrupt and extra interrupt 0. Now IT0 bit also will become 1 and edge triggered interrupt will get triggered. If you observe carefully, I am executing now. The program execution is pointing the fourth line. That means I am doing single step. That means we are initializing the interrupt register IE to enable the interrupts. Just single step. So now you can see extra interrupt is there and extra interrupt 0 is enabled, etc. Now the fifth line is enabling the edge triggered interrupt by making IT0 as 1. You can see now IT0 will become 1, single step. So IT0 has become 1. Now you can see mode 1. Mode 0 means level triggered interrupt, mode 1 means edge triggered interrupt. It has become mode 1. So P3.2 has become edge triggered interrupt. That's all. The rest of the thing remains same. Now I am running this code. So only port 0 is blinking. Now it's very interesting and very important. Now I'm stopping this execution. Now look at the screen. I am making the falling edge now. In P3.0, I'm making the falling edge. Because there is a falling edge, after executing this instruction, it will jump to the ISR. What is the ISR location? 0003. You see? And the program, you can see the data memory location, there is no return address. It was 00. Now the return address will be what? If the program execution jumps to 0003, return address should be 814. No? Now the program counter is pointing 814. Now the program counter is pointing for 814. When I do the single step, because already interrupt has occurred, interrupt is having highest priority. So program counter will be loaded with 0003, but 814 is the return address. So return address will be pushed to the stack to 8th location, 9th location by incrementing the stack pointer as well. Now the stack pointer is pointing 07th location, 07th location of data memory. So whenever the program execution jumps to interrupt service routine, this return address will be pushed to the stack. So 14 will come to the 8th location and 08 will come to the 9th location. This is how the automatically the return address will be pushed to the stack whenever the program execution jumps to the ASR. That we are going to experiment it now. So now I'm doing the single step execution. So program execution has gone to 0003. That means program counter is loaded with 0003, but the return address 811 has come here to the stack. So 811 is the return address. Okay, 811 is the return address. You can see now here in the vector address, it is jumping to 816th location. So in the 16th location, you are toggling port 1. Yes, port 1 has toggled. Again, you are returning back. The program counter is pointing 819. So from 819, it has to go back to 811 because that is the return address. Because after executing the return interrupt, the return address will be popped from the stack. So that is also we are going to experience. So it has come back to 811th location. Now what happened? Main routine only will get executed because ISR will get executed only once for one falling edge. Now you can see main routine only will keep on getting executed. Like in the earlier case, what as long as it is 0, port 1 was blinked. But now if you see, now I am running this code, only port 0 is blinking. Port 1 is not blinking, but port P3.2 is 0. But port 1 is not blinking. Whenever there is a transition from 0 to 1, then also interrupt will not get executed. Whenever the transition goes from 1 to 0, then only port 1 will get toggled. So 0 has become 1. Now, if a tick mark comes means then there is a transition from 0 to 1. In P3.2, there is a transition from 0 to 1. So port 1 is not toggling. But if there is a transition from 1 to 0, port 1 will get toggled. So now you see, I am going to produce a transition. So 1 has become 0. That means it has gone to the ISR. It executed the ISR, come back to the main routine, it is executing the main routine. So every falling edge produces a toggling nature in the port 1. So you can see now there is a falling edge. So there is a port 1 has become FF. Now there is a rising edge, no change. Again falling edge, port 1 will become 0, 0. Now rising edge, no change. Again falling edge, port 1 will become FF. So every falling edge, it goes to the ISR. The program execution is going to the ISR is being justified by the toggling nature of port 1 because that is what we did in the interrupt service routine as discussed. Now we are very clear about falling edge triggered interrupts, and now we are very clear about the level triggered interrupts. So now we are very clear about level triggered interrupt as well as edge triggered interrupts. In level triggered interrupt, we have seen level 0 type of interrupt. In edge triggered interrupt, we have seen the falling edge interrupt. So instead of port 1 equal to 1's complement of port 1, there is a possibility for us to put port 1 equal to port 1 plus 1. That means how many times interrupt falling edge has happened. That can be done by using this. Now it's up to us to relate with an application. So this is the interrupt structure which is available in 8051 microcontroller. Now it is up to us to make use of it. Now I'm running this code. I am making the first falling edge. So the count has become 0. Second falling edge count has become 1. Third falling edge 2. That means every falling edge, the port 1 is incremented because how many times interrupt has happened. Something like that we have written the code. So for counting the number of external pulses without disturbing the main routine, we can use external interrupt 0. So the falling edge type of interrupts can be used for the applications such as counting applications. That's very interesting. So counting the RPM of a motor, counting the number of objects, counting the number of peoples without disturbing the main routine. So until the falling edge comes, main routine will keep on getting executed. Whenever the falling edge comes, program execution will go to ISR and do the increment and it will come back to the main routine. It will continue the main routine, which is fantastic. So to conclude, when we talk about interrupt which is happening in the pin, there are only 4 possibilities: level 1, level 0, falling edge and rising edge. Level 1 and level 0 are called as level triggered interrupt. Falling edge and rising edge are called as edge triggered interrupts. Other than these 4 possible combinations, there is no possible hardware interrupts can exist in any microcontroller in the world, out of which, with respect to 8051, there is a level 0 interrupt is available and falling edge interrupt is available. With this simulation, we have experienced a level 0 interrupt, which is necessary for an applications as long as, and there is a falling edge interrupt which 8051 can support by making IT0 bit as 1, and the falling edge interrupts can be used for the applications such as counting applications. Okay, similarly what we did for INT0, the same thing we can do it for INT1 simultaneously, but INT0 is having highest priority when compared to INT1. So if INT0 is not active, then INT0 will work, and that if possible we'll discuss in the next session. But from this session, we must understand the significance of interrupts and the possibilities of hardware interrupts, out of which interrupts in 8051 microcontroller, how to initialize the interrupts in 8051 microcontroller, how to write the code for interrupt in 8051 microcontroller, how to write the C program, how to test it with the assembly language program, and what is the vector location, what is the stack, and how stack pointer is incremented, how stack pointer is decremented, how level triggered interrupts are executing as for the applications like as long as, how edge triggered interrupts are executing for an applications like counting applications. All those things were experimented and experienced with the simulator, which is a fantastic experience. So it is up to us to make use of these interrupts for our necessary applications. If it is a counting application, better use edge triggered interrupts. If it is an application like as long as, that means as long as the driver's leg is in the brake pedal, the engine should not accelerate. Something like that we can do. We can relate with the application. As long as the brake pedal signal is logic 1, engine should not accelerate. Something like that we can relate with a number of applications as we wish. So level triggered interrupts are recommended for the applications which demand as long as. Edge triggered interrupts are recommended for an application which demands counting applications. That is how it works. I think the hardware interrupt is being discussed very clearly. Thank you very much.